welcome back, my beautiful AP Calculus students. We're going on through examples at least 3, 4, and 5. We'll see how far we can get with the time allotted for this video. Here's example 3. We're integrating using the natural log function. I'm looking at this denominator and I'm seeing that the degree of the denominator is a 1, where the degree of the numerator is a 0. So I'm looking bottom heavy by 1. I'm thinking natural log is going to be in place here. If I were to mentally take the derivative of 4x plus 1, that derivative would be a 4. Although on the numerator I'm looking at a 5. So I am off by a constant multiple. I'd have to get rid of the 4, put the 5 in place, but at least no other x's or any other things are involved. So we're good to go with this. I'm going to go to the side and I'm going to say let u equal 4x plus 1. My du is 4 with respect to x. I don't have a 4 over here. I have this 5 sitting here. I don't want that 5 sitting there, so I'm going to take that 5 to the outside and rewrite this without the 5 sitting in there. And now I don't even want this 4, so I'm going to eliminate this 4 simply by dividing both sides by 4. I get 1/4 du is equal to dx. So I'm going to say that my dx is 1/4 du. I have my denominator as my u. And I can rewrite this whole entire problem in terms of u now. This is 5 times the integral of 1 over u multiplied by 1/4 du. And I don't need that 1/4 sitting there, so I'm going to move that to the outside to join the 5. It'll be 5/4 times the integral of 1 over u du, which is back to my theorem 5.5. I'm just going to go ahead and call that natural log of the absolute value of u plus c. Bring my u back into play, which was 4x plus 1. So 5/4 times the natural log of the absolute value of 4x plus 1 plus c. Make sure that your absolute values look bigger than your ones, okay? Longer, so I can tell what they are. And I think example 3 is pretty well set for you. If I wanted to check this and take its derivative, I could do that mentally, or we could do this together. Find the derivative with respect to x of this whole entire answer. 5/4 times the natural log of the absolute value of 4x plus 1 plus c. The derivative of 5/4 of anything, you just copy the 5/4. Natural log's derivative is going to be a fraction with the power, whatever the natural log is being applied to as your power, on your denominator. And of course, this denominator's derivative goes on your numerator. So the derivative of 4x plus 1 is 4, that's your chain rule, plus nothing because the derivative of any constant is 0. And your 4's divide off, your 5 goes on your numerator, and that is exactly the same thing I had way up here in my anagram to start with, so I'm good to go, and this definitely checks. So much for question 3. All right? I'm going to move on to example 4. So far, 1, 2, and 3 have been real straightforward. We're just practicing the U-substitution, the recognizing the 1 over u to u, and rewriting your integral from x's to u's. All right, here's example 4 now. I'm going to give you a definite integral. So this time we will have to use the fundamental theorem of calculus, and we will have to substitute the upper limit first, minus the lower limit, and then do our subtraction. All right, so this is x over x squared plus 3 dx. Again, you take a minute, you look at your function, you see if you notice anything, and I notice that if I take the derivative of the denominator, I get 2x, and there's just an x on the numerator, so I'm off by a constant multiple, and that keys me into doing a U-substitution. I also notice that the degree of the denominator is 1 degree higher than the degree of the numerator, so I'm probably looking at a natural log here. So I'm going to go to the side, and I'm going to say let u equal x squared plus 3, which always, anytime after you write what u is, please follow it with a du. Du is 2x dx. Well, I don't have a 2x dx, I only have an x dx, so I'm going to get rid of this 2. Simply dividing both sides of the equation by 2, I get 1/2 du is equal to x dx. And that's all well and good. I can go ahead and substitute my u information back into my integral. I'm wondering whether or not you want me to I'm just going to do this. This x dx is 1/2 du, and what's on the denominator is u. However, now, these lower and upper limits over here, these are x values. This is x equals 0, and this is x equals 6. So even though you don't see an x equals next to them, you have to understand that they are x values, and we need to trade those in for some u values. So I'm going to put over here, when x equals 0, u is equal to x squared plus 3. So 0 squared plus 3, which is 0 plus 3, which is 3. So when x equals 0, u is equal to a 3. When I do this U-substitution, I have to replace my lower limit with a 3. And when x equals 6, my u is still x squared plus 3, but this time I want to put a 6 in there. So u ends up equaling 39. This is going to come up here to a 39. And I have 1 over u times 1/2 du. Is everybody okay if I put the 1/2 out here and then write my du right like that? So I just took 2 steps in one, because normally I would put 1/2 du here, and then I would factor my 1/2 to the outside of the integral. But I did that all in one step. I hope you followed it just fine. This now gives me 1/2 times the natural log of the absolute value of u, and no plus c this time. This time, I'm going to take this 1/2 natural log of u, and I'm going to evaluate it using a 39 as my upper limit and a 3 as my lower limit. And when you have brackets like this, you don't really need to draw this bar up and down. You can draw the bar, but it's just traditionally accepted for us to go ahead and just put our numbers there without the bar, so you can feel welcome to do that. All right, well, you know I'm bracket happy, so put your brackets in. This is 1/2 natural log of the absolute value of 39 minus, bracket again, 1/2 times the natural log of the absolute value of 3. And this is what I'm talking about, with sometimes those absolute value symbols are unnecessary or they're useless. They're not providing any purpose. Because 3 is already positive, so I know it's already positive. I don't need to have those absolute value symbols on it already. All right. Well, I don't know what these numbers are off the top of my head. Pretty much all I can do is condense this and write it in a little bit simpler form. I'll factor out the 1/2 from both natural logs, and that will give me natural log of 39. Notice I took the absolute value symbols away. And then minus, this 1/2 is to the outside here, so natural log of 3. And big set of parentheses. Make my natural log a little nicer. All right, well, I have a rule for logarithms that says my exponents are being subtracted. I can go ahead and divide my powers. So I am going to take this up over here. This will give me 1/2 times the natural log of 39 divided by 3. And 3 happens to go into 39 perfectly, giving you 13. So my final answer is 1/2 natural log of 13. And that would be where I end. And I can't turn around and check this by taking its derivative, of course, because this isn't a function notation. This is more of a constant value. When you take the derivative of a constant, you get 0. That's because I have a definite integral, though. This is the area bounded by this curve, whatever this looks like, this function between x equals 0 and x equals 6 with the x-axis. Okay. That wraps up example 4. See how we're doing on time. We're looking at about 9 minutes or so here. All right, I think I will stop this, and we'll move on to a couple of trigonometry examples, okay, with the next video. So this is the end of 5.2 part 2, and we will move on to part 3 in just a minute. Okay? Talent out.